Hello, everyone, and welcome back. In the previous video, we introduced vector spaces. So this is an abstract concept allowing us to quantify the relationship between so-called vectors. Now, the classical example of this is the actual vectors you probably know and love from vector calculus. And those things belong to the spaces Rn, the n-dimensional real space. But what we saw is that there's another kind of vector space that we can talk about that is closely related to everything we've been discussing so far in this lecture series. And that is the space of continuous functions on a given domain. Now, in this case, these are in fact a vector space, and these sort of abstract vectors that we're talking about here are continuous functions themselves. Now, one thing that we know about vectors from, say, calculus or linear algebra is that they have a direction and a length. Now, we're not going to think too much about directions, but what we will think about is the length of this thing. And we have that abstract notion of length, and that comes from the norm of these vectors. We saw that with the continuous functions, the norm we're interested in is that sup-norm that tells us what is the maximal deviation that my function can take from the x-axis. Now, what we're going to do today is we're going to interrogate that sup-norm a lot more. And we're going to ask ourselves, what happens if I take a sequence of functions, so now infinitely many continuous functions, for example, from my vector space, what would happen if their norm went to 0? Well, what does that mean about the function? Or better yet, if I have a sequence of functions and I subtract off another function from it, what happens if the norm of that goes to 0? And that leads us to the first definition that we're going to talk about, and that is uniform convergence. So let's go ahead, let's start talking about this. Again, we'll start with a nice definition. So we will say if f and fn are defined, so are all defined, so there's infinitely many here, that's where the fn comes from, are all defined on a domain D. We say that fn converges to f. Now I'm going to put in the active term here, the new piece of this definition. So it converges to f uniformly, and typically we say on the domain D. So as I said, you always think of a function as a pair, function plus domain, right? If somebody doesn't give you the domain, they didn't properly define the function for you. So this is provided that fn minus f in the sup-norm goes to 0 as n goes to infinity. And in this case, the sup-norm, of course, is taken over the entire domain D, but you can ask yourself, what is actually happening here? Well, when we were taking the sup-norm of a function, we would have our, say, f in here was just 0. So you just had the sup-norm of, say, fn. Now, with that f in there, we are asking ourselves, what is the maximal deviation of fn from f over the entire domain? And so you can see if this thing is going to 0, it means that the maximal deviation of fn from f is going to 0 as well. So this says that it's not just close at certain values of x, it's close at every value of x over the domain. That's what this uniform property comes from. So that's what the sup-norm is measuring. It's a measure of uniformity for this. And it says every point is close. Every fn of x is close to every f of x. And let's take a look at the following theorem. This is a very, very powerful theorem in mathematics. And basically, it says that if you have a uniformly convergent sequence of continuous functions, then the limit itself is also continuous. So that is, suppose fn belongs to the space of continuous functions on the domain D for all n greater than or equal to 1. and suppose Fn converges to F uniformly on D. Then the limit is also continuous. So this is very, very interesting, right? This allows you to approach or approximate continuous functions as long as you have convergence in the uniform norm, that is the sup norm. So how do we prove this? Well, again, a lot of the proof here just comes down to understanding the definition. It's actually a quite straightforward or relatively easy proof. The hardest part is wrapping your head around the intricate components here, and in particular, helping us to understand what it means for convergence in the sup norm. So let's take a look at this. We're going to say let x and d be arbitrary. So you pick any arbitrary point. And we want to show, f is continuous at x, right? And so if we're going to do this, we want to show that f is a continuous function. That means it's continuous at every point in the domain. We say if I pick a random point in the domain, doesn't matter what it is, I'm going to show you that you are continuous there. Okay, that's the goal. So because this is arbitrary, this proof is going to work for every single value as long as I can make it work here in an x independent manner, which is how we've been working through many of our proofs so far. So let epsilon be greater than 0. Of course, we need an epsilon bigger than 0 because we're talking about continuity. We could use sequential definition, but let's use the old school epsilon delta. It's going to do the trick here. So that is, we need to show there exists a delta greater than 0 such that if I find x prime in the domain and close to x, then this implies that their images under F are also close to each other as measured by epsilon. Now, here's what we're going to do. We're going to use the fact that we have uniform convergence. So we're going to say since Fn converges to F uniformly on D, well, then there clearly exists some natural number n such that if I look at n larger than or equal to n, this implies that Fn minus F in the sup norm is less than epsilon over 3. Okay, so let's interrogate that for a moment, right? First of all, I have uniform convergence. That tells me that this sup norm, the difference between Fn and F, is going to 0 as n goes to infinity. So that means, this is a sequence. And so therefore, if I look far enough into it, it's going to be very, very close to 0. Okay, so that's the first piece of this. There exists a capital N such that this is smaller than, and then we can look at what we are smaller than. Now, I picked epsilon over 3. Epsilon is positive. 1/3 of epsilon is also positive. So this still works, right? It's 1/3 of the epsilon that I started with. It's still a positive number. Now, this is an old trick in analysis. You typically see this. Now, what you should recognize from this is epsilon over 3. We're going to add 3 of these things together in order to get an epsilon. You've seen this before with epsilon over 2 in the triangle inequality. We're just going to use the triangle inequality twice to get 3 terms now, and then each one of them is smaller than epsilon over 3. So you'll see what I mean here in a moment. But in particular, this means, so if I fix a value of little n, well, we might as well use that capital N just to be concrete about something. This is true, right? Because the above, this inequality holds for every little n greater than or equal to capital N. So that means if I choose little n equal to capital N, it holds. And the only reason I'm doing this is because I want to pick a concrete value of n. I don't want to say that it holds for all large ones. I need to fix one. Now, since Now, why was it that I needed to fix one? Well, I know that this is in the sequence, and I know it's continuous at x. At x, well, then there exists a delta greater than 0. So I'm just using the definition that this thing is continuous, such that if I take x prime in the domain and close to x, this implies fn of x prime minus fn of x is less than epsilon over 3. There's that epsilon over 3 again. Bear with me. You're going to see where the magic happens here in a moment. But this is important, right? This means I'm taking advantage of the fact that I have a sequence of continuous functions. Remember, I want to show the limit is continuous, but I know that every element of the sequence itself is continuous. So let's take a look. We're going to see that this same delta works for my limit as well. So then if x prime is in the domain and within delta of capital X, then we have, now let's take a look. The thing that we wanted to show that this term right here is smaller than epsilon. Now, how are we going to do it? Well, let me show you how this is going to expand out, because there's going to be adding and subtracting a bunch of terms. So we're going to have f of x prime, and then I'm going to subtract fn of x prime. And then because I subtracted it in there, I need to add it in. So I get fn of x prime, and I'm going to group everything based on who they're going to go with in the triangle inequality here. So that's what these brackets denote. This is minus fn of x. And then the last one, I'll put on the next line. Since I subtracted an fn of x, I've got to add it back in so that all of this just sums up to 0 eventually, or sums up to what I started with. Then what I can do is that I can apply the triangle inequality twice, and that will give me each one of these little brackets inside of their own absolute values. So here, minus fn of x plus the absolute value of fn of x minus f of x. Now take a look at what we have here. I have at a single point x prime, I have the difference of f of x prime minus fn of x prime. Well, clearly that is smaller than or equal to this thing, the supremum. Because x prime is a single value, the supremum is the biggest over all possible values of x. Then I'm going to leave the middle term for a moment. We'll come back to that on the next step. And then the last one, same thing, the difference of fn of x minus f of x. Again, x is a particular, it's a single value. So if I take the supremum over all possible x's, then I get, again, the same inequality that I got from the first piece. Now I know that that is less than epsilon over 3 by my choice of capital N. I know that fn of x prime minus fn of x, if I go back, that's going to be less than epsilon over 3 because I have a continuous function that by my choice of delta. So this gives me epsilon over 3 here. And the last one is the sup norm again. That's smaller than epsilon over 3. Remember, I told you the trick of using epsilon over 3 means I'm going to add 3 of them together. And you can see this is epsilon, which implies f of x prime minus f of x is less than epsilon as desired. And that gives us continuity. All right, so that's the trick. The trick, a lot of the time when you do these proofs, sometimes you have to start at the end and work backwards. So you might want to start with this triangle inequality and then figure out how small, all of these pieces here can be chosen small. You can ask yourself, how small do they need to be chosen so that I can add up to epsilon in the end? I could have done it in really weird ways, right? I could have used say epsilon over 5 plus 2 epsilon over 5 plus 2 epsilon over 5, that would have been fine. It just would have been a mess, right? So there is a piece of this where you're trying to minimize the mess and trying to minimize the difficulty, but also anticipating what's going to happen at the end. So this is where the sort of scrap paper comes in. Okay, so that tells me that if I have a limit, a uniform limit of continuous functions, the limit is itself continuous. Let me give you another type of convergence that you can have. And this is what's called pointwise convergence. So we say that the sequence of functions Fn converging to F, and this happens pointwise on D, so it's different. This is interesting, right? Because this tells us there's two different kinds of convergence that we need to talk about when we talk about functions. If and only if, for all x in D, so if you pick an element of your domain x, the sequence of real numbers. So the sequence of real numbers given by putting x into each one of those functions, right? So I take my value of x and I say, what is each element of my sequence evaluated at x? Each one of those is a real number. So this gives me a real number. This converges to the real number f of x. Okay, so it's important to compare and contrast the difference between uniform convergence and pointwise convergence. Pointwise convergence says that if you pick any value of x and you ask yourself, where does fn of x go? Does it converge to f of x? Well, if it does, then you have pointwise convergence. It happens at that point. What is the difference? Uniform convergence says it happens over the entire domain and at the same rate. That's the important piece. So let me show you an example here. Actually, let's start fresh. Example, let's let fn of x equal to x to the power of n for all x in 0 to 1. Okay, so it's not a function without its domain. In this case, d is equal to the closed interval 0 to 1. Now, I'm going to claim, so we claim that fn does not converge uniformly on 0, 1. Okay, well, the first thing we're going to do is we're going to ask, does it converge pointwise? That's an important piece of this. So we know that if we choose x smaller than 1, strictly smaller, and you fix it, then this sequence, x to the power of n, goes to 0 as n goes to infinity. We proved that, I believe, in the second lecture in this series, right? We did r to the power of n when r is between -1 and 1. So that tells you that if you pick any value of x in the domain that's not positive 1, then the pointwise limit is going to be 0. But if x is equal to 1, then x to the n is equal to 1 to the n, which is just equal to 1. So you get a constant sequence of 1s, which clearly converges to 1 as n goes to infinity. So thus, each fn is continuous on the domain 0 to 1. And fn has a pointwise limit. So maybe let's put this in green to emphasize it. Pointwise on 0, 1. But the question is, what is the pointwise limit? Well, this is where, let's see what f of x is? Well, f of x is what we limit to. So it's going to be 0 if you pick x in 0 to 1, exclusively for 1. And it's going to be 1 if x is equal to 1. So it's a discontinuous function, right? So moreover, f is not a continuous function on 0, 1, right? It's got that spike at the right endpoint. It's 0 everywhere except for one value. It takes on the value 1. Now, why is this an issue? Well, from above, so from the previous theorem, if Fn converged to F uniformly, so since Fn is continuous, then if this was uniform convergence, we would have F being a continuous function, which is not true. Therefore, Fn does not converge uniformly on 0, 1. So that's quite interesting, right? That tells you that you can have sequences of functions that converge pointwise. In this case, you have pointwise convergence to this discontinuous function, 0 and then 1. But it's not uniform. So this is something you have to be very, very particular about. Now, let me give you part 2 of this example. If I change the domain a bit, what if I gave you the same function? So now consider Fn of x is equal to x to the n. But remember, functions come with 2 components, whatever the sort of definition of the function is, but also the domain. So let me change the domain a little bit here, and I'll show you how things change. But now with the domain is just 0 to 1/2. Well, here we have, if you look at the sup-norm difference of Fn minus the 0 function, so this is the 0 vector if you use the language from the last lecture. Well, clearly this is just, the total deviation of Fn, or the largest possible deviation from Fn from the x-axis. But of course, it doesn't take a whole lot to see that that happens at the right endpoint in this domain. And that's just because x to the power of n is an increasing function. The furthest it can get away from 0 is at x equal to 1/2, which is equal to 1 over 2 to the n, which goes to 0 as n goes to infinity. But if you follow that chain backwards, that says, so i.e., Fn minus 0 in the sup-norm goes to 0 as n goes to infinity, which implies Fn converges to 0 uniformly on 0 to 1/2. So this illustrates that the domain really, really does matter, right? The domain plays a huge role in what the results you can get out of these things are. Now, the other important piece that you'll see here is that it's that point x equal to 1 that gives you an issue. Because x equal to 1, if you raise that to successive powers, isn't converging down to 0. So the fact that you don't have uniform convergence comes from the fact that you have slower and slower and slower convergence as you get closer to x equal to 1, right? So if you replace this domain with any number that's between 0 and 1, so you say pick the domain 0 to r, where r is between 0 and 1, then your sup-norm would converge like this. It would converge like r to the power of n, which always goes to 0, but you can see as r gets bigger, as it gets closer to 1, that thing is going to converge very, very slowly. Think about 9 over 10, and then think about 99 over 100 and then 999 over 1,000, those things take progressively longer to go to zero. And that's where the non-uniformity of the convergence comes from in the previous example. The fact that you can get all the way over to 1 here, things are slowing down and there is no sort of uniform rate that everything is converging to 0 at. Okay, now the other thing that you can see with this example is that we already proved that you have pointwise convergence here as well, right? So you have uniform and pointwise convergence to the 0 function. Now we can actually make this clear with a theorem. So if Fn converges to F uniformly on D, then Fn converges to F pointwise on D. Okay, so this tells you that if you have uniform convergence, you can guarantee pointwise convergence. Now let me put a little remark in here. RMK stands for remark. Note that if Fn converges to F pointwise, we do not necessarily have Fn converging to F uniformly. So if you want to pause and think about that for a second, what is it that goes wrong? Well, pause now, but I'm going to continue on. I'm going to ruin the surprise for you. The counter example to this is the first example, right? We saw a function that converges pointwise, but it does not converge uniformly. And the reason it can't converge uniformly is because it has a discontinuous limit. So this is important to keep in mind, right? Uniform convergence is stronger. It implies pointwise convergence. Pointwise convergence is much, much, much weaker. And the best part about this theorem is how awesome and simple and quick the proof is. So observe that for each x in D, we have, again, I used this in the previous proof, Fn of x minus f of x. This is less than or equal to the sup norm between Fn and f. Why? Because this is just the difference between the ranges of these two functions for a single value of x. This is, on the right-hand side, the maximal difference in the ranges, right? So it goes over every possible x. So the equality here would be if that value of x was the one that gave you the maximal difference, the inequality would say, well, this one actually isn't as big as, say, that x over there. So thus, if the sup norm goes to 0 between these things, as n goes to infinity, it follows that Fn of x minus f of x also goes to 0 as n goes to infinity, which implies that Fn converges to f pointwise on D, right? Because that tells us that you have a null sequence if you go back and use some of the nomenclature that we've introduced before, but then we know that null sequences can be rearranged and they can show us that we've got this, in fact, this pointwise convergence. Okay, so that's a nice little result that tells us uniform convergence is way, way, way stronger than pointwise convergence. So what I'd like to do to wrap this up is one more example. And this example, I'm going to do a little bit of cheating. Okay, so technically, we haven't learned the derivative yet. Okay, but I'm going to use the derivative because it's going to make things a lot simpler. So if you wanted to, you could probably do this without the derivative, or you can put this example on the back burner until we learn derivatives. Either or, I want you to bear with me, and we can use, say, if you took a calculus class before this, we can just use your general knowledge of calculus, right? Because this class isn't meant to erase what you learned. It is meant to reinforce it and build a nice foundation underneath it so you understand where everything in that calculus class came from. So let me say, let fn of x equal to x of x to the power of 1 plus 1 over n. So you can see as n gets larger, the power is getting smaller. So then, sorry, we're going to take x on 0, 1 with x belonging to 0, 1. Then it is not hard to see that fn of x converges to x for all x in 0, 1. All right, so we have pointwise convergence to the linear function. So that is, i.e., fn converges to x pointwise on 0, 1. Okay, so that just comes from the fact that that exponent is converging to 1. This is, you can just sort of see this very, very formally by letting n go to infinity and 1 over n go to 0. Now, we claim this convergence is actually uniform. So we want to prove that we have uniform convergence here, right? So again, think back to that theorem that I have at the top. We don't know. All I've shown is that we have pointwise convergence. That does not tell us anything about the status of uniform convergence here. And so the question is, do we have uniform convergence? And how can we prove this? Well, here's what we'll do. Let's let gn of x equal to f of x minus fn of x. Okay, so this g function is quantifying the difference between the limit f and the sequence fn. And of course, where the limit, so where f of x is equal to the pointwise limit x. So note, so let's do some noticing here. Gn of 0 is equal to f of 0 minus fn of 0, which is equal to 0, right? If you just put 0 into all of those functions, you get 0. And gn of 1 is equal to f of 1 minus fn of 1, which is equal to 0 again, because you have 1 minus 1. And gn of x is greater than or equal to 0 for all x in 0, 1. Okay, so I'm just listing off a few little properties here. This is just going to make things a little bit easier. And again, I'm not trying to nullify the things that you learned in calculus. You can use that intuition you built up to try and understand this function. And I highly, highly recommend it. All right, so this fact that this thing is positive, you can just use nice calculus notations here. Okay, now there exists, so also there exists xn in 0, 1 such that g prime of x, sorry, gn of x is equal to 0 if and only if x is equal to xn. So for each value, or for each value of n, there is only one critical point, and gn of xn is a maximum. So again, you can use, if you want to, you can use Rolle's theorem to get that this thing is a maximum, or you can just use basic calculus. Again, I'm sort of skirting over the details here because we haven't done derivatives in this class. So we're just going to assume that you can just use your regular old derivative rules. Moreover, xn, so again, just go in, set the derivative equal to 0. You get 1 plus 1 over n to the power of n. So what was the point of doing all this, Jason, right? You seem to be doing a lot of work to arrive at, I'm not sure what. So now this is going to help us, because if we look at this, the difference in the sup norm between f and fn, Well, this is equal to the sup norm of Gn, right? So just by definition. Also, Gn is a positive function and it has a maximum at xn. So the sup norm of Gn is equal to Gn of xn. That just comes from the definition of this function. And now I can actually calculate what Gn of xn is. I'm going to just give it to you after doing a little bit of arithmetic here. So I had a little bit of fun before this. You can have your own fun with it. Now this is a sequence of real numbers, right? So I want to show that this thing goes to 0. Well, now maybe we'll have to make a little side note here. Maybe you might not remember this limit. I kind of hope you do, but it might have been a while since you've seen math. 1 plus 1 over n to the n. Well, actually, let's start with the first piece here. 1 plus 1 over n to the n. This is one of the most famous limits in all of mathematics. One place where this comes up is in business mathematics or financial mathematics. This is as compounding periods go to infinity, right? So this is continual interest payments. And you might remember now that this thing converges to that number e, right? Everybody's favorite number in calculus, e to the x, it's our favorite number to take derivatives of. This thing converges to e. So then this tells us that 1 over that, this converges to 1 over e. Okay, so that's just a little refresher on what happens here. Then this converges to 1 over e times 1 minus 1 over 1, which is equal to 0. So therefore, if we look at what we just proved, f minus fn in the sup norm converges to 0 as n goes to infinity, which implies fn converges to f uniformly on the interval 0 to 1. So it took a little bit more work, but in this case, we could explicitly calculate out what the sup norm of the difference is between these two functions, just maybe using a little bit of calculus, asking ourselves what is the maximum in this region. But nonetheless, after that, it turns into a fairly straightforward calculus endeavor, right? This limit that we saw here, this is a sequence of real numbers, so we can evoke what we did for the previous few videos on sequences of real numbers. It might have taken a little refresher, those limits that are in blue there. We saw those maybe in an introductory calculus class. Maybe this is the first time you've seen them. But these are very, very famous and well-known limits in mathematics. And in this case, we get uniform convergence. So we got both pointwise and uniform convergence. Now, what we've seen in this lecture is that there are two ways for a sequence of functions to converge. That is uniform convergence. Every value of x converges at exactly the same rate. That's what the uniform norm, the sup norm, is capturing. Or just simply pointwise convergence. So if you just pick a value of x, then fn of x is converging to f of x. And this is happening everywhere in the domain, but it might take longer at different parts of the domain. Now, this is probably a little bit different, a little bit confusing to you, because when we talked about sequences, there's only one way for them to converge. It's sort of pointwise because there's only one point for each value of n. The difference here with functions is that there are infinitely many points because you have a range for this function that is any value of the domain you put into it, you get a range. And you're asking, when do these ranges converge, right? That's really what fn minus f is asking you. And so the question is, does it converge uniformly or does it converge pointwise? And what we saw in here was a number of examples how you can disentangle these two situations. And we saw some interesting results that told us, uniform convergence is way better. It's way stronger because you get pointwise convergence for free from it.